Hello, AP Chemistry students. This lesson is going to be involving the stoichiometry of precipitation reactions. We're going to start by looking at a precipitation reaction between two solutions. We're going to focus on determining the mass of the precipitate that forms between those, and then determine the molarity of each ion that then remains in solution. So the first thing is you need to be able to actually write the precipitation reaction, which is just air double replacement reactions, by writing the formulas correctly and balancing it correctly, which we have here. We've also identified that the barium sulfate's our precipitate. I've also just noted in here from the information up top, basically our volumes and our molarities of the two solutions that we're going to be dealing with. So first things first, we need to figure out how much precipitate forms. So this is similar to the beginning of the year, just that we said we're using our solution in order to figure this out, but we're going to use stoichiometry. So I'm going to first look at the fact that I have 0.100 liters, and I'm going to just focus on my first reactant, potassium sulfate. So then from there, I'm going to use my liters to use my molarity to figure out my moles. So just like we've done before, except in this case, we're going to be using our volume and our molarity to figure out moles. So get it into moles. Okay, so now I'm just like where I would normally be in stoichiometry. I have moles of my potassium sulfate. So now I can use the mole to mole relationship that for every 1 mole of K2SO4, I need 1 mole, or I'm going to produce 1 mole of my precipitate BaSO4. Okay, from there I can just figure out my grams. You could stop there if you wanted for each of these and then go on once you find which ones you're limiting. But I'm just going to go ahead and calculate both out to grams. So that's just my molar mass of my BaSO4. Okay, when you go ahead and plug those in and you round to the 3 sig figs that you start with, I get 2.33 grams of BaSO4. Okay, now I need to check my other precipitate. So I have my 0.100 liters of my barium nitrate. I'm going to use its molarity, which is also, or is 0.2 in this case. So for 1 liter of it, I have 0.2 moles of my barium nitrate. Okay, using the mole to mole relationship here, for every 1 mole of BaNO3, I can get 1 mole of barium sulfate produced. And then I'm just going to use the same molar mass here for barium sulfate at 233.44 grams. Okay, and when you plug that in and round to 3 sig figs, you get 4.67 grams of BaSO4 produced. So we know then that we can only produce 2.33 grams of my barium sulfate. So that is my answer. That also tells me here that K2SO4 is going to be my limiting reactant. And then the barium sulfate is going to be the one in excess, which is going to be important for the next piece of this. Okay. One other thing to notice is some of this with mole to mole, you could probably narrow down and figure out the limiting reactant based on that. But here I'm just showing you the full work in order to get to the grams of the precipitate. All right. So for this next part, we're now going to focus on the ions that remain in solution after this precipitate has formed. So I've already wrote out just a little bit here to start us off with. There's a couple different ways you can do it. I've kind of minimized the amount of work that I'm showing in mine by working it through this way. You'll see in some of my other answer keys a lot more work shown, but this is one way that I think streamlines it a little bit more as I've done this over the years. So if we go back to starting off with our 2 reactants, I'm just figuring out the moles of each of those reactants. So now I want to know how many moles I have of each ion in solution. So if I think about breaking this part up, okay, I have my K plus, my potassium ion. Now, for every 1 mole, and I'm going to kind of show my stoichiometry here, for every 1 mole of K2SO4, I get 2 moles of K plus. So I'm just going to multiply that amount there to get my concentration, or my K plus ions, equal to 0.0200 mole. Sulfate is just a 1-to-1. So this would be for my SO4 plus ions. This would then be 0.0100 mole. If I do the same thing here with my barium ions, this is a 1-to-1, so this is going to be 0.0200 mole. And then I have to be careful here with nitrate. Okay, for every 1 mole of the barium nitrate, I get 2 moles of my nitrate ions. So for my nitrate ions, this is going to be 2 times that. So I'm going to have 0.0400 mole. Okay, now what's actually in solution and that we have to deal with? So when you look through these, we need to think about the fact that the K2SO4 was my limiting reactant, okay, which means that the SO4 ions that are in the precipitate, these are no longer in solution. Those are completely consumed. So those aren't in there anymore. However, these spectator ions remain in solution after the reaction. So I am going to be using this. So these remain in solution after the reaction. Okay, if I look at my barium nitrate, which is my one in excess, okay, these 2 ions here, I'm going to first off note that my nitrate ions, okay, these are also spectator ions. These are going to remain completely in solution after. So both of those I can quickly go ahead and find my new concentration of. It's going to be the barium ions. So the ions that are in the precipitate that come from my reactant in excess that I'm going to have to figure out how much was consumed and then how much is left over. Okay, so we have a couple things that we're gonna have to do with that. So let's first just deal with the 2 spectator ions and just find their new concentrations. Now, one important thing to note here is that as we find all these concentration of ions after, for all of our new molarities, okay, we must use the new combined volume. Okay, so in this case, our volume, we had 0.1 liter of our potassium sulfate solution, and then we also had 0.1 liter of our barium nitrate solution. So for this new one, we have 0.2 liters of our new solution. So we can go ahead and just quickly find our concentration of our potassium ion and our concentration of our nitrate ions. Okay, going back up here, we know we have 0.02 moles of potassium ions in the solution that didn't react with anything. That's now in a 2-liter solution. When you go ahead and divide that, you're going to get a 0.100 molar concentration of our potassium ions. Okay, kind of doing the same thing for nitrate here, except I'm going to use its number of moles, which is 0.4. So I have 0.0400 moles of my nitrate ions that didn't react with anything in their new 2-liter solution. When you go ahead and divide that, I'm going to get my 0.2 molar concentration. Okay, so we found 2 of the ions that we need. The last one is going to be dealing with our barium ions. So in this case, I'm going to write this out a little bit just so you have some notes on here. We're going to, for barium, okay, I'm first going to have to look at the amount that was consumed. Okay, how much reacted with the limiting? How much reacted with the limiting? So we know just from our work above that we had from our limiting 0.01 moles of it. So I'm just going to start with that. So I have 0.0100 mole of my K2SO4. Okay, 1 mole using my balanced equation of my K2SO4 reacts with 1 mole of BaNO3. NO3 2. Okay, I'm going to go right to our barium ions. So for every 1 mole of BaNO3 my barium nitrate, I get 1 mole of Ba2 plus that was consumed to make the precipitate. So when you go ahead and calculate that out, you get 0.0100 mole of Ba2 plus consumed into the precipitate. Now I want to figure out basically how much is left over. So amount left over. So I started with my 0.02 moles up here. So that's how much was initially present. Minus the amount that was consumed and made into the precipitate, which was my 0.0100 mole. And when you subtract those two, you get 0.0100 mole of Ba2 plus ions that are going to be left over. So now this amount, that is now how much of the barium ions that are still in solution. So when I say left over, that means still in solution. Okay, I can now go ahead and figure out the concentration. So my concentration of my barium ions is going to be the amount that remains in solution, my 0.100 mole, divided by that new volume, so that combined volume of 0.2 liters. And when you go ahead and find that, you get 0.0500 molar solution. So just so hopefully I can get these all up there. These are my 3 ions that remain in solution: potassium, nitrate, and barium. And these are their final concentrations after the precipitation reaction. So one thing I do want you to think about is look back over this and think about, number one, how is this similar to stoichiometry that we've done earlier in the year? But then also think about how to make sense of figuring out, when you look at that initial reaction, how to figure out, okay, what's being consumed, no longer in solution, that's in regards to your precipitate, and then what's left over. What are your spectator ions? How do we figure out the concentrations of those? How do we figure out about the excess ion that didn't fully form precipitate that's left in solution? So these will definitely take a little bit of time. I'm going to go ahead and make an example or a video of the next example as well, but I want you to at least initially try that out on your own.